Hi, so today I want to talk to you about nanowires. Here we see an image taken from this cool article up here describing some nanowires that were used to help kill cancer cells. And these are nanowires that have been doped with magnetic nanoparticles on the end. But moving on, first, before we talk about that really cool stuff, I think we need to do a little bit of a review of some introductory physics concepts so you'll be kind of up to speed on what I mean by all that. So here we have a review of the classical model of conduction, and we're going to cover a little bit on current and drift speed. And so if you consider a current carrying wire, and we have our charge carriers, we're just going to call them a charge Q right now. Of course, in metals, the charge carriers are mostly electrons. So here we have this current carrying wire. The cross-sectional area of the wire, which in this case for a cylindrical wire would be a circle for the cross-section, and you have the charge carriers moving through in the presence of an applied electric field, and they're moving with what's called a drift velocity, v sub d, in the direction of the current flow. We're going to look at a little slice of that current carrying wire with some distance here, delta x. And so of course the charge carriers are going to move that distance delta x in that's going to be equal to the drift velocity times the amount of time delta t that it takes them to move through that distance. You have a certain number of charge carriers per unit volume, and that's dictated by what kind of material you have. So for example, for different metals in the periodic table, they might donate one or more of their electrons per atom to the free electron gas. And that arises to a certain density of charge carriers throughout the volume of the material. And of course, that's a material property that depends upon the density of the material and the number of charge carriers per unit atom that are donated. Okay, so that's kind of the review. And the idea is that we're going to talk about the definition of the current. Now remember that the current is defined as a charge in coulombs per unit time that's flowing through your conductor. So you have a number of coulombs per second, which gives you your amp. Okay, so first, if we're going to set up a value for our average current, which is going to be a delta Q over delta T, or certain coulombs per second, then we have to first define what the delta Q is. So the delta Q will be the total charge that passes through that cross-sectional area at the end of our little slice in a time delta T. So the total charge delta Q is the number of charge carriers per unit volume times the cross-sectional area, and then times that delta x, and then we're going to multiply that times the charge carrier charge Q. Okay, so that's the number of charge carriers in that volume. Now, the drift speed, v sub d, the speed at which the carriers move, is going to be our delta x divided by our delta t, and you can rearrange that and plug in for delta x in our equation for delta q. And if you do that, then you get delta x is equal to v sub d times delta t, and then you can rewrite that. So that you have delta q is equal to n times a times v sub d times delta t times q. And then if you want the current, you're going to divide that delta q by the delta t, and then that cancels out there, and you end up with an expression for your average current, nq v sub d times a. Okay, so here remember, n is the number of charge carriers per unit volume, q is the charge per charge carrier, v sub d is the drift velocity, and a is that cross-sectional area. Okay? So that's our expression for the current that we're going to work with later in the lecture. Now, if you think about what the motion of charge carriers look like in a typical conductor, like a metal, a bulk metal, then you think of sort of a zigzag pattern, okay? The zigzag motion is the motion all over the place. So the charge carrier moves through, it scatters off something, it bounces off, it goes some other direction and some other direction and some other direction. So the motion looks very chaotic. But on the whole, if there is an applied electric field, you'll have a net motion in one direction. Okay, and the net motion of an electron, for example, would be opposite to the direction of the electric field, because remember, your electrons want to move up those electric field lines. Okay. So in the presence of a field, in spite of all those collisions, the charge carriers move along the along with the drift velocity v sub d, the electric field exerting forces on the conduction electrons in the wire, and it causes them to drift along rather slowly and create a current. Now, it's true that each individual electron doesn't move very fast. However, remember that the field is applied pretty much instantaneously throughout the conductor, and so once you apply that current, you've got electrons moving all along the length of the wire all at once. And that's why when you flip a light switch, the light turns on pretty much instantaneously from when you flip the switch, and not, 10 hours later. So if you assume a copper wire, and in a copper material, 1 free electron per atom contributed to the current, and if you have a 12 gauge wire carrying a current of 10 amps, and you were to calculate what the drift velocity would be, you might think that it would be fast, but instead, no, it's actually a really slow speed, 2.2 times 10 to the minus 4 meters per second. Now, this may seem slow, and you might think, well, if I did it for a different metal, it might be, larger. Not really. For typical densities for your metals, 10 to the minus 4, 10 to the minus 5 meters per second is a typical drift velocity. So these drift velocities are really slow, but like I said, the field is established throughout the material at the speed of light, and so you get current flowing throughout the wire basically all at once when you turn your switch on. Now, to review, there's a couple of forms that you're used to seeing of Ohm's law. The original form is this one, J is equal to sigma E. J here is the current density, which normalizes for the width or diameter or area of the wire. So J is the current I per unit cross-sectional area of the wire. And that's because, of course, fatter wires carry more current than skinnier wires, and you want to normalize out for that. Okay, so J, that's J, current density, is equal to sigma, which is the conductivity of the material, times E, where you have the electric field. Now, sigma is a constant that's independent of the field producing the current and only depends upon what kind of material you have. The resistivity is the inverse of the conductivity. So rho, which is often used as the resistivity, is 1 over sigma. Okay? Now, most metals obey Ohm's law, and materials that obey Ohm's law are said to be ohmic. Semiconductors do not fall into this class of materials, nor do insulators. Okay? And it's also worth stating that Ohm's law is for bulk materials, and it doesn't necessarily apply to nanoscale materials. If you use Ohm's law and go with the classical model of conduction, then you can come up with a couple of expressions for your conductivity and your resistivity. Your conductivity expression then turns out to be N times Q squared times tau divided by the mass of an electron. And of course, the resistivity is 1 over that. Now remember, N is the number of conduction electrons per unit volume. Q is going to be the charge of your charge carrier, usually E, 1.602 times 10 to the minus 19 coulombs. Tau is the average time between collisions, and M is the mass of an electron, 9.11 times 10 to the minus 31 kilograms when your charge carrier is an electron. Now, let's go back to this tau. Tau is the time between collisions, and it's related to the drift velocity, okay? So the drift velocity is equal to what's called the mean free path, which is the distance between collisions, okay? How far you can expect your charge carrier to go before it undergoes a collision, which is usually on the order of nanometers or tens of nanometers in most bulk metals, okay? And then you divide that by the time between collisions, and that gives you your drift velocity. So it's worth noting that the electrons can be going really fast in between collisions. It's just that they don't go very far or for very long in between them, okay? So the conductivity and the resistivity, yet again, they depend upon the material and not on the strength of the field. All right, so another important thing that we need to review from classical physics before we go on and talk about nanoscience is the Hall effect, okay? So remember that in introductory physics, you learn that a current carrying wire or a moving charge in a magnetic field experiences a force described by the right-hand rule and known as Lorentz force law. So that is equal to F is equal to QV cross B, where Q is, of course, your charge, V is the velocity of your charge, and B is the magnetic field. You can rewrite that for a current carrying wire as F is equal to IL cross B, where I is the current, L is a vector that has the length of your conductor pointing in the direction of current flow, and B is the magnetic field. Now, this right-hand rule force causes a phenomenon known as the Hall effect in conductors. So in the Hall effect, basically what you do is you place a current-carrying wire, or it's easier to see this effect if you have kind of a metal strip, okay, with some width to it in a narrow sort of structure. So if you place that strip of current carrying material within an external magnetic field, then what will happen is, according to the right-hand rule, the charges that are moving through that strip will move to opposite edges in the transverse direction of your strip. Okay, so if you see here in this little diagram, you have the primary current, which is basically means which directions the electrons are flowing in this material. So they're moving through here. You have a magnetic field that's pointing upwards, and then the charges will separate according to that right-hand rule, and you'll have a net positive charge here on the left-hand side and a net negative charge on the right-hand side of your conductor. Okay, and that's the Hall effect. So that separation of charge causes a transverse voltage in the metallic strip, and that's called the Hall voltage, and you can measure that Hall voltage. So what happens is when you turn your current on, the charge will start to build up as long as you have that external magnetic field, and the charge will build up until such time as the voltage builds up so that the electric field force counteracts the magnetic field force, so that you have Q times V sub D, your drift velocity, times your magnetic field, equaling QE, okay? That's because the direction of the electric field and the force on the charges due to the electric field is going to oppose the direction from the magnetic field, okay? And so you get that situation where you have a Hall voltage that eventually builds up that counteracts that Lorentz force law QV cross B force on the electrons. And then you have a stable situation. And that happens pretty fast. Okay, now remember that your voltage is related to your electric field. Delta V is equal to the integral of E dot ds. And so if you were to write what your Hall voltage would be, then it would be equal to your electric field times the width of your strip. So if you plug in then for your electric field in that QV sub dB is equal to QE equation, then you would have QV sub dB is equal to Q times your Hall voltage divided by the width of your strip. All right. Now, the Hall voltage can be used in something called a Hall probe, which you've probably seen or will see in some experiments that you use to measure magnetic fields. Okay, so it uses that Hall voltage output to measure the magnetic field strength, and so then you can solve and get that your Hall voltage is equal to the width of your strip times the drift velocity times your magnetic field. But since it's easier to measure a current than it is to measure a drift velocity, then you can plug back in to that expression for the drift velocity instead with a current. And if you do that, then you get an N times E times V sub D times W times T, which is the thickness of your strip. Because remember that your cross-sectional area, A, of your current carrying object would then be equal to W times T, the width times the thickness of your strip. Okay, now remember that Q here is the charge in your charge carrier, so I'm just going to go ahead and sub in and say that that's E, which is 1.602 times 10 to the minus 19 coulombs. All right, so you can get an expression for your Hall voltage that's proportional to the current through the strip times the magnetic field, and then divided by N times E times T. All right, so you can also rewrite this expression for the Hall voltage in terms of something called a Hall resistance, which would be the current that you would measure times the resistance, using that sort of consequence of Ohm's law, V is equal to IR. So in that case, you'd have the Hall voltage is equal to the current times the Hall resistance, like so. Okay, so that's our review. Hopefully we're done. Now that's all the knowledge that you're going to need in order to understand the rest of the lecture, I hope. All right, so here we go. So that was the classical Hall effect. It's a macro scale effect. It's used all the time in Hall probes to measure magnetic fields, and now you're up to speed. Now the quantum Hall effect is a little different, okay? In the 1980s, a man named Klaus von Klitzing, which may be one of the best names ever, was conducting experiments on this quantum Hall effect. What he was doing was he was using a very thin 5 to 10 nanometer thick semiconducting film in a strong magnetic field. And when I say strong, I mean 2 to 10 Tesla. Remember, a Tesla is an enormous unit. Your MRI machines have magnetic fields that are within this range, and you can also pick up cars with electromagnets in junkyards with magnetic fields of this size. So these are big fields. All right, so he cooled these materials to about 1 Kelvin. Remember, liquid helium is 4 Kelvin, so this is pretty impressive. And then what he did was he found that if he plotted the Hall resistance versus magnetic field strength, B, ranging up in value, that he could see defined steps in his conductance value or in his Hall resistance values. All right, so basically he was applying a voltage or applying a current to these semiconducting materials, and he was measuring the Hall resistance with different values of the magnetic field, and then he was plotting that out, and he saw these steps. Okay, so this is an illustration of the data that came out, and he noticed that these steps, these plateaus, had very defined values. Okay, so the values were h, Planck's constant, divided by s, an integer, divided by e squared, the charge on an electron, 1.602 times 10 to the minus 19 coulombs squared. Okay, so these integer steps, h over e squared, became known as the von Klitzing constant, r sub k. And if you solve for it, this value is about 25,813 ohms. Okay, so basically, this was showing that instead of a continuous value of the resistance, okay, instead of a continuous value, which you would expect from V is equal to IR Ohm's law, instead of that, you get quantized values under certain conditions where you have these very thin films, high magnetic fields, and low temperatures. For this work, he actually won the Nobel Prize in, I believe, 1985 to demonstrate this quantum Hall effect, which had been previously predicted but never before observed. All right, so this is a revolutionary idea. This shows that your resistance, and hence your resistivity, and hence your conductance, is actually something that is quantized, okay, when you have these very thin films. In other words, when it's on the nanoscale in terms of the thickness of your film, okay, of your Hall effect strip, if you shrink that down to the nanoscale size, right, then you get quantization of the conductance of your material, which is pretty impressive. So the quantum Hall effect is the result when you confine electrons in one dimension. Remember, they were free then to move in a plane, so they were free to move in 2 dimensions, all right? A nanowire is defined as a material that confines the charge carrier motion in 2 dimensions, okay? So basically, they're only free to move along the axis. Carbon nanotubes have been shown to act as nanowires, but I do want to say that there's others. There's other materials, okay, like silicon, gallium nitride, zinc oxide. They've grown nanowires out of a lot of different materials using chemical vapor deposition, also metals, lots of different materials, and the sizes can range from a few nanometers to up to about 100 nanometers in diameter, with lengths up to about 100 micrometers long. So here's some images of some zinc oxide nanowires down here at the bottom, and some silicon nanowires up here at the top. So you can see it's not just carbon nanotubes that we're talking about here. Now, they exhibit some pretty interesting properties that differ from the macro scale or bulk predictions that you'd get from your classical or even your bulk models of conductance. And the reason for that is, of course, because of their size. What this does is it forces them to become confined, right? And the consequences of quantum confinement are that you go from a bulk metal situation where you have these energy levels, but because you have so many atoms, because you have so many choices, the energy levels are spaced super close together so that the delta E between any of these levels is really tiny and it looks continuous. So that's your bulk situation. But if you start to confine the materials, then that doesn't happen anymore, and you're back to a situation where the energy levels are discrete, and you can tell the difference between neighboring energy levels. There's actually decent sized jumps, okay? So you're not going to be able to look and see a continuous situation anymore. You'll see more of a discretized energy level situation, which leads to quantization of your conductance values. Okay, so that means that we can't use the familiar formulae that we got in our introductory physics courses anymore. V is equal to IR, for example, the Ohm's law consequence, that's not going to shake out like you would expect. And you can't figure out what the resistance of a particular conductor might be using the Ohm's law type prediction of R is equal to rho L over A, where you have your resistivity times the length of your conductor divided by the area. That might not work anymore either for a nanowire, okay? What happens instead is that for most materials, as the wire's diameter decreases, the conductance of the nanowire also disproportionately decreases. Now, this is for a lot of different reasons. First of all, remember that for a nanoscale material, your surface area to volume ratio goes up, right? What this means is that you get something called edge effects, which means that your surface atoms behave differently than your bulk, and you get more scattering at the surface than you do from your bulk. Okay, so that's your edge effects. There's increased scattering of your conduction electrons because they're confined more and they can't go very far, so they scatter more. I mean, that kind of makes sense. So here, what you see, this is a plot that I took from this cool little website right here that I encourage you to visit. Here, the conductivity is shown and plotted versus the temperature, but also the different types of colors here indicate the different diameters of the nanowire, so that you can see here's your bulk prediction in red, and then your conductivity goes down when the wires are 20 nanometers. These 20 nanometer diameter wires, this right here is the doping, so you can see these have been less heavily doped, so they're not as good conductors, but you can definitely see the dependence there on the diameter of the wire. And then here it drops down a bunch for 10 nanometers. Okay, so as the diameter drops, the conductance disproportionately drops. So that's what I'm getting at here. You can also see that as the temperature increases, the conductance drops, but that's a much lower effect compared to how much they jump as you drop your diameter. All right, so that's been seen. Another thing that's been seen is that the conductivity itself is actually quantized, and it depends upon the diameter of the nanowire that you have. So there's this cool quantity that they call the conductance quantum that for some reason, I don't know why, is symbolized with a capital G with a lower subscript naught. So it's G naught, okay? The conductance quantum is 2 divided by the von Klitzing constant, okay? So 2 E squared over H, and that's your conductance quantum. So if you see here, this is a plot taken from a cool article by Foley and colleagues, which was published in the American Journal of Physics in 1999. I've placed this article on our course website so that you can read it. It's an easy read. It was designed to be an undergraduate level experiment, sort of a senior seminar experiment, if you will, for what we do here. Okay, so what they've done here is that they have put these nanowires in between 2 electrodes, and then they applied tension so that it's stretching the wire out, so that makes the diameter go down. Actually, sorry, other experiments have done that. This one, what they did was they disturbed them. They had these 2 fine gold nanowires in loose contact, and then what they did was they oscillated the nanowires so that the effective cross-sectional area of the wire changed. I'm sorry, so that's what this one did. Okay, so what they did, they had a constant voltage of about 10 millivolts applied between these 2 gold fine nanowires, and then they oscillated it, and that changed the effective diameter of that wire, and then they measured the current that came out, and from the current they calculated the conductance of the wire. And then you can see then that they got these discrete steps as they were oscillating their wire, and those discrete steps corresponded to integer jumps in the conductance corresponding to integer jumps of G naught, the conductance quantum, okay? So this is because the transport of the electrons is affected by the number of available energy states that there are. Remember, it goes back to that idea of the quantized energy states, all right? Thinner wires means that there's fewer available energy states, and what that means is the conductivity is going to drop in discrete steps as your wire gets thinner. Okay, so conductance is discretized, which is really pretty interesting. One way to wrap your head around this is to kind of go back to the Heisenberg uncertainty principle, okay? So let's look at the energy time uncertainty principle, where you have delta E, delta T is proportional to Planck's constant H. Okay, so let's plug in for these values. Remember that your current is charge divided by time. So here, let's assume that we're getting just conduction of, say, 1 electron. If you're going to have a discrete conduction of current, that would, the most discrete you can get is 1 electron. So 1 electron divided by the time that it takes to move that through your little wire, tau. Okay, so we're going to let tau equal our delta T in our Heisenberg uncertainty principle. So tau then would be, if you set it equal to your current expression, delta T would be equal to E over I. Okay? So now, the energy, delta E, that we're going to plug into our Heisenberg uncertainty principle is the kinetic energy that that electron gets as it's accelerated through the applied voltage. Okay? So that would be equal to your charge on your electron times the voltage, going back to another introductory physics expression. Now we're going to take those two expressions for delta E, delta T, and plug them into our Heisenberg uncertainty principle. So when we do that, we get E times the voltage is equal to E divided by the current, or E squared times V over I. Now your conductance, okay, is going to be inversely proportional to your resistance. So using V is equal to IR as our expression, 1 over R would equal to G naught, which would equal to I over V. So if you plug that back in, then you get V over I is equal to 1 over G naught. And so you have that delta E delta T is equal to E squared divided by G naught is approximately equal to Planck's constant H. So if you solve for G naught, you get G naught is equal to E squared over H. And then you can understand the conductance quantum as the idea that that factor of 2 in there, 2 E squared over H, is because there's 2 available spin states of the electron and each one of them can move. So you can have 2 electrons in each energy level. All right, so that's kind of my hand-waving, sort of intuitive understanding of our conductance quantum. I hope that helps. So in addition to sort of quantized values of the conductance, something interesting happens to carbon nanotubes, and that's known as ballistic transport. So single-wall carbon nanotubes have been shown repeatedly to have quantized values of conductivity and experience ballistic transport of the electrons during conduction. In ballistic transport, what happens is your electrons don't scatter, okay? They don't scatter due to impurities, defects, or from lattice vibrations. This phenomenon has been shown to occur when the length of the conducting wire is actually shorter than the mean free path of the electron in that material, right? So if your wire is shorter than you would expect the electron to go before it scatters, then basically there's no scattering, and if there's no scattering, then there's pretty much no resistance. So that's ballistic transport. So this has been shown. The first time that it was shown was by this group at Georgia Tech, a group of colleagues, and it was published in a paper known as Carbon Nanotube Quantum Resistors, and so I'm going to talk about that paper for the remainder of the lecture. So what these folks did was they took some carbon nanotubes that they had made, attached onto the end of a scanning probe microscope, and then used the existing piezo in the scanning probe microscope to apply an oscillatory motion to the carbon nanotubes. And the carbon nanotubes during this oscillatory motion were repeatedly dipped into a little pool of mercury, okay, a liquid metal. They also did it into a pool of gallium, but we'll just talk about the mercury for now, okay? So when they did this, they applied a voltage in between their carbon nanotubes and their mercury, and every time they dipped it, they would monitor the current, okay? So they monitored the current during the dipping. And then from that, they calculated values of the conductance. Okay, so it's worth mentioning that the nanotubes that they used were multi-walled nanotubes that were 2.2 micrometers long, some of them, and 14 nanometers wide, okay? So they were very nice nanotubes, and they have, this is a TEM image of the end of the probe that they used, shown here. So very careful to quantify all their work. They also used voltages that ranged from 10 to 50 millivolts for most of the experiments, and they showed the data for that. Okay, so here's some of their data. In this first plot, plot A, what they are doing is showing you they dipped this multiple times. It had a period of motion of about 2 seconds, and this is one of the traces that they found. On the y-axis here is plotted the conductance, G naught, and you can see that every time it was dipped into the little pool of mercury, the conductance that they measured jumped up, and they saw a value of 1 G naught every time they dipped it. So that very clearly demonstrates that for the nanotube, for 1 nanotube, you get a value of 1 G naught. Now here they show a sort of number of traces, a histogram, and you can see that for 250 traces in their histogram, they have a very sharp histogram that peaks at 1 G naught. So that's plot B. Now here in plot C, this is a trace of the nanotube contact with 2 major plateaus. And this is when you have 2 nanotubes together. So this is 1 nanotube at 1 G naught, and 2 nanotubes gives you 2 G naught, and then you can see from there maybe you have 3 and it goes on up. So each nanotube that works as the conductor, each time you get more than 1 nanotube, maybe they had several nanotubes bundled together, for example, it would jump in integer steps. So this very clearly demonstrates that they're getting quantized values of their conductance for the nanotubes. Now they also took the voltage to 6 volts, which is very high when you're only applying it to a few nanotubes, right? Remember that for most of the time their voltages were in the range of say 10 to 50 millivolts. So if you take it to 6 volts, then you're really applying some voltage and you're getting some high currents or high current densities through those nanotubes, okay? In fact, the current densities that they were getting corresponded to 10 to the 7th amps per square centimeter, which is really high. Superconductors, for example, have conductances of 10 to the 5th. So this is 2 orders of magnitude larger current density than you get out of some superconductors, right? Now, another really fascinating thing about that wasn't necessarily that they were able to do it, but that they were able to do it without totally vaporizing their nanotubes. You would expect at these high currents that there'd be some resistance in the nanotube itself that would raise the temperature high enough to actually vaporize the nanotube, because it doesn't take a super high temperature to do that, and the theoretical resistances and the theoretical temperatures that they mapped out said that, you know, if you consider it sort of classically, the temperature should get above 10,000 Kelvin, which should be more than enough to vaporize these nanotubes. And the fact was that they saw that the power dissipated when they did this was only about 3 milliwatts, okay? So what that means is that the nanotubes themselves were conducting the current ballistically, basically with no resistance, and that any resistance that did occur occurred in the attachment of the nanotube to either side, right? So it was dissipated, the power was being dissipated when it was attached to the SPM, or maybe when it contacted the mercury at the bottom, and that was where the power was being dissipated, not in the nanotube, because if it were being dissipated in the nanotube, it would heat up and be vaporized, okay? So that was their evidence for ballistic transport, all right? So that's some of the interesting things that I wanted to tell you about nanowires. I hope you enjoyed it. Remember that at any time you can pause the lecture if you feel like I'm going too fast and really digest it. So don't hesitate to do that if you get confused, or go back and watch sections of the lecture over again if you need to hear it a second time. I'm also available here if you have any questions, and I'll see you next time.